This video unifies 3 recent papers on influence functions for modern language models. Our goal is to answer one concrete question: when a model behaves a certain way, which training examples actually caused it? Training data attribution matters for transparency, debugging, safety, and data curation. If we can rank influential training sequences for a specific output, we can inspect model behavior mechanistically instead of guessing from prompt-level observations. We proceed in 5 parts. Part 1 reviews classical influence function mathematics. Part 2 uses the 2022 paper to ask what object influence functions truly approximate in deep networks. Part 3 scales influence analysis to very large models. Part 4 covers TrackStar and fact tracing at retraining scale. Part 5 synthesizes actionable lessons. Classical influence functions come from robust statistics and approximate leave-one-out retraining with a first-order parameter perturbation. If we upweight one training point z by a small epsilon, the parameter shift is approximately minus epsilon times inverse-Hessian times that point gradient. For a test query z-test, influence on test loss is the directional derivative along that shift. So influence is approximately negative gradient on z-test transposed, times inverse-Hessian times training point gradient. This is the canonical Hessian-corrected dot product form. Bottleneck is the inverse-Hessian vector product, not the formula itself. In modern models, the Hessian is huge, often ill-conditioned, and may contain negative curvature. So practical methods rely on approximations, damping, and matrix structure assumptions. Influence methods are exact or near-exact in convex or linearized regimes, but mismatch can be large in nonlinear deep networks after finite-step optimization. That gap motivates the 2022 paper. If influence functions are the answer, what exactly is the question they answer? Paper 1 decomposes the discrepancy between practical influence estimates and leave-one-out retraining into multiple terms, then measures those terms experimentally across architectures and training stages. The key empirical message is nuanced, not binary. Your central object is the proximal Bregman response function, or PBRF. Intuitively, it asks, what parameter update best accounts for removing a point while staying close in predictive behavior under a Bregman geometry? Influence estimates often align better with this proximal response than with strict leave-one-out retraining. One reason this reinterpretation matters is damping and Hessian surrogates. When we stabilize inverse curvature with regularization or Gauss-Newton-like approximations, we change the implicit objective geometry. So a mismatch to pure retraining is expected. The algorithm is solving a nearby but different problem. So the 2022 paper reframes the conversation. The question is not just whether influence equals leave-one-out exactly. Practical question is whether influence-based rankings answer intervention and debugging tasks robustly. Under that lens, the methods remain informative. Paper 3 scales influence analysis to LLMs up to tens of billions of parameters. 2 bottlenecks are tackled: approximate inverse-Hessian solves and fast candidate training sequence gradient computation. For curvature, they use EK-FAC, eigenvalue-corrected Kronecker-factored approximate curvature. The idea is to approximate second-order structure blockwise, then correct spectrum quality enough to preserve ranking utility while dramatically reducing compute. For gradient throughput, they use TF-IDF filtering to narrow candidate sets and query batching to amortize computations. This turns what would be a prohibitive all-to-all procedure into a practical pipeline for large studies. At that scale, they analyze generalization phenomena, sparsity of influence patterns, abstraction changes with model size, math and code behaviors, cross-lingual effects, and role-play dynamics. Influence maps become an empirical lens on how capabilities are actually assembled from training data. One especially important limitation they report is phrase order sensitivity. Influence can collapse when key phrase order is flipped, even if semantics seem close to humans. This highlights brittle lexical coupling in what might otherwise appear like deep conceptual generalization. Paper 2, TrackStar, focuses on scalable influence and fact tracing for pretraining scale corpora. The setting is extreme: multi-billion parameter models, over 160 billion tokens, and no corpus subsampling requirement. TrackStar combines several practical corrections. Optimizer state correction accounts for training dynamics not captured by naive static approximations. Task-specific Hessian approximation sharpens causal ranking for the objective of interest. Normalized encodings stabilize comparisons across heterogeneous examples. A central result is a misalignment between factual attribution and causal influence. Classical lexical retrieval, like BM25, can better find passages that explicitly state a fact. But influence methods can better identify examples that causally shift model predictions. The paper also reports a hopeful trend. With larger model and token scale, influence aligns more closely with attribution. That suggests scaling can smooth part of the mismatch between lexical evidence and causal training dynamics. Qualitatively, influential examples are not all direct fact copies. Some reinforce priors on relations, entity patterns, and naming conventions that support the same answer indirectly. So influence reveals distributed support structures, not just nearest textual paraphrases. Now unify all three papers mathematically. Influence ranking is always a bilinear form between query gradient and training gradient under an approximate inverse curvature metric. So changing the metric approximation changes what notion of causality you are measuring. That directly answers the 2022 title question. If influence functions are the answer, the question is not only leave one out retraining. The broader question is which examples are causally consequential under a chosen optimization geometry and approximation budget. A practical workflow is: choose target behavior, compute stable query gradients, use scalable curvature approximation, rank candidates, and then validate causality with targeted ablations or retraining checks. Do not overtrust a single ranking. Common failure modes include lexical shortcuts, curvature approximation drift, optimizer history mismatch, and distribution shift between query tasks and pre-training objective. Open problems include sequence-level causal decomposition, faithful multi-example interaction effects, and tighter alignment between influence scores and mechanistic circuit explanations. Another frontier is combining retrieval style and influence style evidence in one calibrated causal framework. The big picture is clear. Influence functions have evolved from a fragile classical diagnostic into a scalable empirical science tool for LLMs. As long as we are explicit about the target object, curvature approximation, and validation protocol, these three papers together mark that transition.